Hi everyone, I'm Karthik, Principal Solution Architect with Kinetica, and today we're going to talk about the benefits of using a GPU database for machine learning and deep learning. So before I get started, a quick point on Kinetica, right? So we were incubated in the US Army back in 2009, right, as a project to help detect terrorist threats activities. So what the NSA wanted to do was look at 200 plus sources of data, streaming data, analyze it. These could be devices, drones, social media data, cyber data, around 200 billion records that needs to be processed. They obviously need real-time actions, decisions on the data. So our founder, Nima and Amit, incubated this in-house, and we decided to go to market commercially in 2012, right? So that's where this started from. So what we'll do today is talk a little bit about where we are now, what are the different capabilities, how we help with machine learning, deep learning, and how the power of the GPU helps with this. Show of hands, how many people today use GPUs at your current projects? Okay, a couple, right? So for those who haven't used GPUs, the power of the GPU is in the parallel processing power and the sheer number of cores, right? So a GPU, an average GPU has anywhere from 4,000 to 6,000 cores. An average CPU has anywhere from 8 cores to 40 cores. We've seen new processors with 100 cores, but an average GPU has 6,000 cores. Imagine if you can use your GPUs to take your existing compute that you have and break it down and accelerate them. That's what our product does, right? So what we've seen is we've seen a speed up of around 100x gains over traditional RDBMS applications. We've seen a gain of anywhere from 10x to 1,000x based on the type of queries that we've run. We've seen a reduction in the total cost of ownership of as much as 75% for traditional RDBMS infrastructure costs. What we'll also do is to keep this a small audience, right? So we'll keep it interactive. So I don't want to go over all my slides. So let's go over some demos to see actual Kinetica working, right? So that'll be a little more fun, right? So what I'm going to do is to try and slip in a few demos as and when I'm talking, so that way we'll keep this a little more interactive. And if there are any questions, please feel free to ask. Okay. So the evolution of data processing, right? So I started out back in 1998, and at that time, you essentially had standard analytics, right? So you had your database, you had your 3-tier model, you had simple reporting structures. I used crystal reports back in the day. Since then, we've evolved tremendously. You had the concept of real-time analytics back in 2005. Right? You had concepts of Hadoop, maybe a couple of years back. Even right now, Hadoop is still very prevalent. The concept of real-time analytics. Right now, where we are currently seeing the market grow is for high-speed analytic processing using machine learning, deep learning. The whole conference is about AI, right? To be able to run all of these algorithms in parallel with the power of the GPUs, right? So we've grown from simple reporting to much more complex deep learning algorithms, but the goal is to be able to execute them very, very fast. So what Kinetica allows you to do is it gives you a GPU accelerated in-memory database that's columnar, that requires 0 tuning, and that requires no indexing, and the ability to run your queries very, very fast, right? So we essentially have a visualization layer, a visualization pipeline that's built in, a geospatial layer that allows you native GIS support, a streaming layer that's built in, and integration with traditional technologies like Hadoop, Spark, Tableau, JDBC, ODBC, and 7 different languages. And I'll get into a little bit more of those. But from a high level, we are an in-memory GPU accelerated database. So with that said, let's quickly, let me go over one more slide, and then I'll go into a demo. What are our strengths? So we cover 4 different use cases. The top one is fast OLAP, right? If you have a query that requires a table scan, if you have queries that do group bys, that do joins, Traditionally, we've seen that if you have a join query against billions of rows of data, right? You have a table with, let's say, 80 million rows and another one with 70 million rows, and now you want to join based on multiple keys that are not the primary keys or foreign keys. Complex queries, wildcard searches, those usually take a lot of time. Those are very, very expensive, right? So we help with, we help use the parallel processing of the GPUs to accelerate these queries, right? So it's high performance, low latency analytics on very, very large data sets, right? So that's our primary use case. The second one is based on where we came from, right? So based on our background with NSA, the native geospatial and visualization pipeline, any geospatial queries, geospatial joins, geospatial geofencing, right? So we were talking with a customer earlier who wanted multiple geospatial fences on top of the data. So let's say you have your spatial data, and now you want to have a geofence based on, let's say, zip code. Then you want to have another layer on top of it based on your where your customer shops. And now you want a filter and query your data based on multiple layers. You can do things like that. And then finally, we'll concentrate a little more on the in-database analytics piece, the convergence of AI and BI, right? So traditionally, if you have your data scientists who come up with, let's say, machine learning algorithms, it could be simple algorithms like linear regression, random forest algorithms, or more complex algorithms like Monte Carlo simulations, gradient boosted trees, anything like that. Anything can be taken. Your data scientist comes up with your algorithm, your business users want to use it. You can take your algorithm, deploy it in Kinetica, and export it to the world in any different language that you want, right? So you can converge your AI and BI using the UDF feature, and we'll cover that a little more in detail. And finally, we have customers who use a traditional BI tool such as Tableau, maybe MicroStrategy. Traditionally, tools like Tableau are pretty fast, but in certain cases, when you actually have to source the data from the underlying database, they have problems if your data set is large. In case your query itself does a table scan or does a join or does a group by or has to process large amounts of data, we act as a speed layer in front of your database, in front of Tableau, to enhance your queries. Okay, so with that said, let me quickly break and let's go to some interesting stuff, right? Some demos.
So one quick question. I think one question.
Sure, go for it.
I mean, the speed layer that you talk about over things like Tableau, I think we've seen some other databases too. But one of the things that we keep running into again and again is this concurrency limit. We have different entities that give that performance, that kind of a performance. So sooner or later, we run into concurrency limits.
Absolutely.
How do like that here, or?
Absolutely. So how do we tackle concurrency? So so we are an eventually consistent columnar in memory database, right? So if you have a lot of our customers have multiple users, multiple threads that go and access the data. So let's say if you have 20 threads that go and access the data, but let's say 19 of them are reading, one of them are writing, a thundering herd problem, right? So what would happen in our case is we allow all your reads to go through without any blocking, no tracks, no transactions, no logs. You read uncommitted data as long as the commits don't pass through, but that when one thread commits, then all your 19 threads are going to read the updated data. So no blocking, no locking, eventually consistent. So all threads will read until your write completes. So we tackle concurrency issues a number of different ways. Again, there's variances of that, but that's the usual that's the usual pattern that we usually see. Okay, a quick point on the cluster itself that I'm going to do the demo on, right? So this is a 8-node cluster, right? That's on super micro boxes, right? So each box has 256 GB of RAM, and it's backed up by 3 K80s. A K80 is GPU chip, right? So it's a pretty decent sized cluster, and right now we can. I mean, this was the cheapest cluster that we could find back in the day, right? So this is an 8-node cluster, right? So you have much stronger boxes today. So take my performance numbers that I'm going to show you with a pinch of salt. You can actually beat these numbers very easily. Okay. So let's look at the data, right? So what I have here is a billion row data set. This has 4 billion rows, 4 billion, 84 million rows, right? And as you can see, if I refresh this, it goes through the Wi-Fi that's there in this hotel. But you can quickly see that you're able to paint the screen in a few milliseconds. Right? It started to paint the screen, and it's painted the screen. And this is live, live Twitter feeds that are coming in as we speak. So if I hit the live update button, you can actually see the tweets that are coming in and the count going up. So you can see that the data is painted very, very quickly, again, due to the power of the GPUs. Right? So let's perform some analytics on it. So let's try to draw a geographic boundary on this data. So let's choose, let's say, I don't know, let's say a freehand polygon, right? So let's draw a polygon around the eastern United States. Let's cover Florida. There we go. So what I was able to do in a few milliseconds is filter down from 4 billion, 84 million rows to 513 million rows right there, right? 513 million rows. And all of this was done within a few milliseconds, right? Let's do more queries, right? So let's do a text search, and let's search for O'Reilly, right? That's where we are today with a capital R. OK, let's see how many tweets there are today with the subject O'Reilly. How about that? 596 people are tweeting, right? So let's click on some, and hopefully they're fit for work. So. OK, there you go. OK, so some of them are good, but some of them are. So at the end of the day, it's Bill O'Reilly as well. So there you go. So at the end of the day, you can see the text search, the text O'Reilly was there in the tweets, right? But the goal is you're able to now filter down from 4 billion, 84 million records to little less than 600 records in a few milliseconds, right? So let's look at a few more aspects to this. I came from a development background, and one of the things that's very, very close to me is SQL, right? So let's say if you want to write SQL on your data sets, right? Usually what we've seen traditionally is SQL that does a table scan is very, very expensive, right? SQL that does, let's say, a count, min-max, standard deviation, variance, average, right? These require a complete table scan of a table. So what I've done is I've written a query that does a count, sum, average, min, max, standard deviation, variance on multiple columns on a table with 4 billion rows, right? 4 billion records. And if I run this, it's going to do a table scan, and then the query completes in 72 milliseconds, right? Right there. Right? And then just to show you that the data is not cached, if I run the query again, the last 3 digits are 491, right? So if I run it again, it's 580, right? So essentially, in the time that it took me to run the queries, the second time I got around 80 tweets, I would say, right? OK, so that just shows you the power of GPUs, right? How fast you can run queries on large data sets. And then very quickly, wanted to show you another join that I wrote. So this is, again, something that I designed so that it translates to be an expensive join. So I did 4 different things that I thought were expensive. So I did an average, I did a join, I did an average, that's a table scan. I did wildcard search, right? So wildcard search based on the genre, the movie genre, and then we did a group by. Right, I did a group by, order by, wildcard search, and an average. So this obviously would require a table scan. So this has around 20 million records, and this query returns in 52 milliseconds. Right? So just to give you a power of how fast this is. OK, so let's quickly go to another demo, and then I'll go back to the slides. So one of the things that we've seen, especially in machine learning and deep learning, is the ability to rinse and repeat. Right? So what we've seen is when you have models, you have the sorry about that. OK, so you have the need to execute certain machine learning algorithms on your model, but then you'll have to run it again and again with different data sets. Right? So there's a need for all of these executions to happen very, very quickly, and that gives you the bandwidth to run multiple models in a very short duration of time, right? So that's where the power of GPUs come in. And to demonstrate that, what we have here is a taxi data set that's public. That's New York City taxi information on where taxi rides originated from. So slicing and dicing the data, that's very quick. I've already showed you that, but let me show this one more time. So some of the logic behind these dashboards are very, very expensive. So for example, this does the average cost per mile, and then it groups by the vendor ID, right? So let's choose vendor VTS, right? So now I boil down to 513 million. This does the average, the total sum amount, and it does a group by the payment type. So let's say I choose cash. So when I choose a specific thing, all my dashboards are going to reflect that, and it's going to come up. So all my dashboards change based on my selection, and I'm able to get my results in a few milliseconds. Let's choose a timeline, right? So I'm able to filter down to maybe 185 million records. Next, let's do a geospatial query on all the taxi rides that originated from, let's say, the Wall Street region, right? So now I have a geospatial query that boiled down to 43 million records in, again, a few milliseconds. Notice that all my filters still remain, right? So my vendor, my payment type, and my timeline still remain. Now, the concept of rinse and repeat, right? If I have to rerun my same model, but let's say I don't want to run it on my Wall Street data, I want to run it on my Upper East Side data, but I want to keep my same filters. So if you have to run things like that, all you have to do is edit this, drag and drop this, and run the model again, and it's going to execute it immediately, still keeping the same filters and getting your data for you, right? So that gives you the advantage of running your libraries very, very quickly and very fast. Exactly. Right. So no, but you're exactly right. So there is a need for comparing and I think the question is there is a need to compare and contrast the data across various sources, across various geographical regions. And there's multiple ways that you can do it, right? So you can obviously, if you have all of that data in one geomap, then you can compare and contrast that data. But if you have it in multiple maps, then what you could do is you can correlate them, you can join them, you can perform your analytics on that. But you're exactly right. We support all of that. Just wanted to show you one more quick thing. So in case you want to change your region, you can do that on the fly as well, right? So again, it's going to execute your queries very, very quickly. Okay, so let me go back to the architecture very quickly. I'll cover this, and then we can go back to the demos. Okay, so how does Kinetica work? Okay, so behind the scenes, so Kinetica is a distributed in-memory store. So this shows 4 nodes. So data is stored in your system memory. It can also be stored in GPU memory. It can also be stored on your persistence store. Data is also stored in your disk for any persistence needs. We came from a lot of people from our company came from an open source background, so we have extensive connectors to the Hadoop ecosystem, right? So Kafka, Spark, Storm, NiFi, SQL, I showed you SQL, so that's one of my favorites. And then from an API perspective, we support 7 different APIs. C, C++, C#, Node.js, Python, JavaScript, Java, and of course REST. Everyone supports REST. Right? And then from a UI perspective, there's the connectors to Tableau, Power BI, and MicroStrategy. Okay, so let's quickly go to how the data exactly is, and then I can show you the UDFs. So just to quickly show you how your data looks like, I showed you the cluster itself. Okay, so this was the cluster itself, right? So if I click on the data tab, there's a list of collections. So just to show you how huge the cluster is, if we go back here, so this has around 25 billion records in this cluster, right? A little 1.71 terabytes, right? Then the data itself, So you have your collections just like any other database. So if I choose one of these, I usually choose the Twitter data. So this has 4 billion records. So if you look at this table, you have your, it's just like any other table, right? You have your timestamps, your columns. The columns could be, you know, anything of your choice. You have your basic data types, long, float, int, string, you know, all of the good stuff that comes with it. And then your properties, right? So you can set primary key, foreign key, timestamps, you know, all of the good stuff. Now, one key thing here that you have to note is I have not set a primary key or a foreign key here. So this is going to be a brute force scan. And you can see the index column there is blank. So all the queries that I've done right now, it's a brute force scan. No indexes, no primary key or foreign key set. So if you actually had set it, you'll probably get much better response times. Okay. So let's quickly talk about, so that's how the data is, right? So let's move on to the concept of a UDF, right? So we spoke about fast data, we looked at queries. Let's talk about UDFs and how that helps enhancing machine learning and deep learning. So let's quickly talk about the concept first, and then we'll go into a demo, right? There's a couple of demos that I would like to quickly show. Okay, so the concept of excuse me. Okay, so the concept of a UDF is bring your own compute to Kinetica. So your compute could be anything simple like, let's say, a linear regression algorithm, a simple regression algorithm, a random forest algorithm, or anything more complex like a Monte Carlo algorithm, a gradient boosted tree. What you can do is you can take all of these distinct compute sets, your libraries, register them in Kinetica, right, and allow your business users to invoke your libraries in any way, shape, or form that you want, right? So for example, if you had your, let's say you had a Python script that you need you had a Python script that does linear regression, and you would like to parallelize it, you would like to leverage the power of the GPUs. You can take that script, register it in Kinetica, and call it in any way, shape, or form you want, right? You could do that with Java, you could do it with Python, you could do it with C++, or you could do it with CUDA, right? So one of the great things about our product is to leverage the power of GPUs, you don't need to know CUDA, right? You can use your traditional programming languages and simplify them, parallelize them, and use the GPUs. Right? So that's the basic concept of an UDF, right? You can take your functions, deploy it in Kinetica, and call them. And now let's see how it works. I'll show you how it works, and then we'll go back to this slide. Okay, so what I have here is incoming stock tick information, right? So I have my stock tick information that can be segregated by sector, symbol, industry. That's painted on this dashboard, right? So let's say slicing and dicing the data, I've already showed it to you in a couple of other dashboards, but that comes standard, right? So let's say I choose information technology, I choose semiconductors, I choose NVIDIA, right? So yeah, so NVIDIA stock has risen tremendously over the last couple of months, couple of years as well, as Rima knows. But this is data from 2005, so take it with a pinch of salt, right? So, so let's choose NVIDIA, and now what I would like to do is to execute a UDF, a function that calculates the volatility and the value at risk for this data, right? So very quickly, for people who don't know what volatility and value at risk is, so this is so volatility is a financial term that calculates the amount of uncertainty about the stock that you own, right? Whether for every $100 that you spend on a stock, would you gain or lose money? And obviously, higher the volatility, the more riskier is the security. And then value at risk is again a measure of the risk of investments, right? So these are functions that we got from our partner NVIDIA, and that's essentially used by regulators in the financial industry. There's multiple functions. There's coefficient of variance function as well. Right now, I registered these two, but this could be any functions that you want, right? So these were written in C++, but you can write this in any language of your choice. So what I did is I combined these two functions, and I've put it in as a UDF under Kinetica, right? And just to quickly, I'm a technical guy, so just to show you how a UDF looks like. Oh, sorry, I went to the wrong screen here. Okay, here we go. So when this comes up, I'll show you what I've registered. There you go. So I've registered the risk management UDF here. You can actually create and register your UDFs using this UI. So if you are a Power Business user and you have your algorithm with you from your data science teams, you don't need anyone to you don't need anyone from your engineering team to help you register your function. You can just go here, create a new function, execute a new function, pass in your parameters, pass in your libraries. If you have 10 libraries, you can pass all of them here, and you should be good to go. Okay, so I've registered your risk management UDF. Now let's quickly look at how this works. So I've chosen my sector, I've chosen my industry, and I've chosen NVIDIA. And let's see what would happen if I decided to invest $100 in NVIDIA. Right? So if I run my proc, it's actually going to execute the variance and value at risk calculation on the stock. And it actually tells me that for every $100 that I invest, I would gain or lose $3.3 back in 2005. You'll actually gain, right? Now we know that. But back in the day, that's the volatility, right? Okay, so that's one example of a UDF. The second example that I would like to quickly do is for those technical guys in the room, there's Python. There's a Python notebook called Jupyter, and we executed this for one of our retail customers. So this looks at car sales information over the last 10 years and projects the car sales in 2018 and 2019 for specific make and models, right? So when I worked with a few financial services firms, they said they use linear regression today for some of their models, and I found that surprising. It's actually a pretty effective algorithm. So this is a linear regression algorithm that is used to project the car sales going forward. Okay, so the way this is a little bit technical, so bear with me, but we'll try and complete this pretty fast. So what I'm doing is trying to establish a connection with my server, and I'm trying to filter based on the make and model, right? So right now I'm choosing Ford as my make, and you can see that I have a significant amount of data. So the data itself, if you look at it, is the car sales based on the years from 2007 onwards, right? So it says, at least the first row says that for the year 2007, for the month January, you sold 400 cars, right? And so on and so forth. So you get the idea here. So let's go and let's do some projections. So what I did here is, oh, I went too far. Okay, never mind. So what I did here is so I created a UDF. I called it linear regression, and then this is my table name. That's the new car sales. Excuse me. And my output table name is projected new car sales, right? And I was able to execute that, and I filtered based on the quantity, the make, and then the quantity that of what's sold in 2018, right? Whatever is greater than 0, obviously. So you can now see that the average. You can now see that let's say for Ford Montijo, right? So for the month of January, the average was 247, but the projected sales in 2018 and 2019 reduces, right? And if you had projected a few years in advance, you might see that it might grow closer to 0. So it might not make sense investing more in Ford Mondeo. I don't think it exists anymore, that model, but you get the point, right? So essentially you can predict future sales based on past sales. The Ford Focus is obviously selling a lot better. And you can also predict your sales based on certain months, right? Obviously during the holiday season, Christmas season, You probably have more discounts, you probably have more sales, end of year sales, than maybe sales in February or March. Okay, so that was the linear regression example. So with that said, let's talk about a couple more examples of advanced analytics of where we've seen this being used. I personally worked with a vehicle testing company for car races, right? So this company manufactures car for F1 racing in London, and they essentially needed to run certain algorithms very, very fast. So they have tests that collect millions of data points from their wind tunnel and road tests. So they have their car, they have their racing car. They go through a plethora of tests on the car itself. So they run their car through the wind tunnel, they put water, they have sensors on the tires, they have sensors on the brakes, on the wheel itself, alignment. So they run thousands of tests and they run the tests multiple times on the cars to find out the best optimum tire pressure, optimum fuel level, and a variety of different things. Now the challenge is each of these calculations run very, very fast, right? It takes 1.5 seconds to run one calculation. But the challenge is they need to run these calculations in parallel, and they need to run these calculations, thousands of calculations over time. Now, if your end result isn't complete in a certain amount of time, then they can't tune the car properly before a run, right? So that's where the power of the GPU comes in. So what they were able to do is to take all of this data, feed it to the GPUs, and enhance their performance. So now you can A, parallelize your calculations, and B, use the power of the GPUs to make it a lot more faster, right? So that's one advantage of using machine learning with vehicle testing. The second is in the financial industry. So I've personally been part of a number of these. Pricing and risk calculations is a classic example. Asset management, market risk, another great example. I worked with global equities teams where you have to consolidate trade information. You have to do end-of-day valuations based on certain spot ladder changes. All of these are very, very fast when you use GPUs to accelerate them. And then finally, in the pharma world, genome signaling, right? So essentially, if you want to identify new signals and accurately predict drug test results, you need the ability to process a large amount of information very quickly. So you see the theme here, right? So essentially, there's a large amount of information you want to you want to predict behavior, identify threats, opportunities, and accurately predict results. So that's where we come in. So with that said, I'm almost at the end of my time. So what I'll do is break. But before I break, I just have a couple of quick things to talk about. The first is we have a booth here, booth number 20, right? So we are giving out T-shirts, the cool T-shirt that I'm wearing, right? So it says Kinetica here, and in the back it says, "Don't send a CPU to do the GPU's job." So please stop by, right? It's available for free, and we also have a small workbook, right, on the various use cases of GPUs. All right. Cool. Thank you. Any questions? Yeah, sure. Where I don't suggest? So we are very, very good with OLAP use cases. We are not in the OLTP space, right? So if you're doing some transaction processing, that area has been well covered. So that's not something that we currently it's not a very good fit for us.
So how do you see this architecturally coexisting in a heterogeneous environment?
Yes, I don't have that architecture slide here with me right now, but that's part of my deck. So usually, the way we work with a Hadoop ecosystem or any ecosystem is you you traditionally have a concept of a data lake, right? So usually we have systems like Oracle, like DB2, any of your Hadoop systems that resides as part of a data lake. We act as a speed layer on top of data lake that ingests from, let's say, a Kafka, Storm, NiFi that feed into your BI tools, right? So we are traditionally a layer on top of your data lake that interacts with the other customers.
Copy from existing data marts, data warehouses to Kinetica?
Yeah, so you're exactly right. So we ingest data into Kinetica. We have a multi-thread, multi-headed, very, very fast way to ingest data. We can do ingest rates as high as 1.4 billion records a minute. But you're right. So we exist as a layer, as a speed layer on top of Kinetica. Please.
About the UDF, usually like Kubernetes and Xcode or script organization databases, right? If you're like queries, aggregations, mass sort, that kind of thing, those functions are naturally, just can be naturally distributed. But what if end-to-end example regression, or maybe attributes, whatever, those can be parallelized, right? What if UDF that you create was not natively supported? Like,
Correct.
whatever data
That's a very good question. So the question is, there are inherently some functions that can be parallelized. There are inherently some functions that cannot be parallelized. So what do you do in systems? Yeah, exactly right. Right. You're exactly right. And I'm not here to say that they can be parallelized. So this was the question that I asked my CTO Nima as well during a dinner. So you're exactly right, right? So there are a few things that we work very, very good at. So if you do group bys, if you do joins, if you do aggregate functions. So what we do behind the scenes is single instruction, multiple processing, right? So we parallelize the instruction set, we send it to the GPUs, and GPU does its magic. But there are a few cases where we cannot parallelize it. Like if you wanted to do an order by and you wanted to process the data in a specific order, those are things that cannot be parallelized. So we do a couple of things, right? So we do the parallelizing part, and then second is we use the power of the GPUs. So, but to your point, there are a few use cases that's not the case, and that's just law of physics. So that's true. I agree with you. Cool. Thank you.